Thank you to the students for having organized this session there, and to all my colleagues who are working so hard in this school despite the circumstances. And of course, thank you, Kaisa, for your patience. This visit to Malaga probably was not as we all expected it, but thank you very much for being there and your disposition to everything. Just let me introduce you, Professor Kaisa Miettinen from the University of Jyväskylä in Finland. She and her team are working for very long in multi-objective programming in general, and in interactive methods in particular, and have got many results, papers, and also the DESDEO system, which hopefully we're going to see working today. So thanks a lot, everyone. And Kaisa accepts questions during her talk. So if someone wants to make a question, or in the room you want to make some question, please use the hand here. You raise it, and then we'll stop, and you can open the microphone and make any question you want. Okay. So I think we can start. Let's go ahead. Let's see how this works. Thanks a lot.
Thank you so much, Kuro, and very good morning to you all. Greetings from my hotel room in Malaga. So we are not that far, but anyway, we are connected. And once I start sharing my slides, I will not see the hand. So I hope that somebody will give me a warning whenever there is a question, because I will be very happy to answer whatever needs to be clarified during the talk. And let me see how I managed to share my screen. Is it looking okay?
Yes.
Yes.
Very good. So I would like to very warmly thank the organizers of this PhD school for inviting me. And on this map, you see where I come from. Where we now are, it's not quite visible in the map, but where you know where we now are. And I'm planning to tell you something about some interactive multi-objective optimization methods, and then the DESDEO software that we plan to be applying this afternoon, so that you all can have an experience of working with it. As far as the contents of my lecture is concerned, I will remind you first a little bit about why we need multi-objective optimization methods and why it is so important to prepare the model for the problem well before we have the opportunity to start solving the optimization problem. And then I will introduce some interactive methods, in particular Nimbus and Nautilus Navigator, that I have highlighted here because they are the methods that have been implemented and made available for you to be tested later today. Then I will say a few words about visualizations and applications and some experiences with different decision makers applying interactive methods in various domains before I conclude. So, basically, whatever application domain of optimization we consider, it is very typical that we identify different perspectives that characterize the goodness of the decision that we are making, and we need to consider them simultaneously to be able to make a good decision. For example, if we are buying a car and we only pay attention to the price, it is very likely that it will not be a reliable car. It might not have the properties that we actually need the car to possess. So we need to consider various perspectives simultaneously. In many cases, people still, in many application domains, people still tend to think that they need to articulate everything as a single objective function. For example, converting everything into money and then optimizing a single function. But by doing that, we have the risk of missing some relevant information about the problem. And these trade-offs or interdependencies of the objective functions might reveal some very useful information for us. So that's why formulating problems as multi-objective optimization problems has a lot of benefits. Many times the problem can even be computationally easier to solve. And as an example of a special case, it might be that the problem has so demanding constraints that the feasible region is empty. For example, I have dealt with that kind of a problem related to continuous casting of steel. And in the normal setting, if that happens, that there is no feasible solution, then we would say that there's no optimization problem to be solved. That's the end of the story. But we can convert the problem to a new one where we minimize constraint violations as objective functions, and in that way find solutions that are least violating the constraints, and we gain a lot of insight and understanding about the problem and can identify solutions that violate the constraints the least. So that's a kind of an example of a special case of the problem where we end up solving a multi-objective optimization problem. And overall, the task of multi-objective optimization to me in this talk is to help a decision maker to find the most preferred solution, the most preferred trade-offs among these typically conflicting objective functions. I tend to assume for simplicity today that the functions are to be minimized. Of course, whether we minimize or maximize depends on the nature of the function to be optimized. Typically, we maximize profit and we minimize costs, etc. And it's just about changing the sign. No difficulties in there. And we have these decision variables that are limited by constraints that articulate the feasible region or feasible set. And then we map these feasible variables with the objective functions to the space of objective functions that in my notation has k dimensions, and we get k-dimensional objective vectors. And typically in multi-objective optimization, we pay a lot of attention to the objective vectors, because typically the dimension of this objective space of objective functions is lower than the space of the variables. But of course, both spaces, the decision space where the variables are and the objective space where the objective function values and objective vectors are, of course, they are both important. And we have this definition of optimality that differs from single objective optimization because we have several different solutions that can be seen to be somehow optimal. They can be called Pareto optimal, they can be called efficient, they can be called non-inferior, they can be called non-dominated, they can be called Edgeworth Pareto optimal. There are many names for this, but the whole idea is that we can't improve any function without impairing at least one of the others. And for example, in this figure, we have all these solutions denoted by the red color. They are Pareto optimal. And this is the case where we have two objective functions to be minimized, for example, price and maintenance costs. So the question is, which of these solutions is to be selected as the final solution? Because whenever we have a problem to be solved, we typically need to have a solution to be implemented in practice. And that's why we need different methods to support the decision maker with. Very important key notations are ideal and nadir objective vectors. By the way, do you see my mouse when I move it?
Yes.
Excellent. So this point here is a so-called ideal objective vector. So we obtain it by minimizing, in this case, remember that was the assumption, both of these objective functions individually, and the individual optima gives us this point. Of course, as we can see, it is not feasible, it's not possible to get this kind of a solutions, but it gives us information about the best possible values that can be obtained for the objective functions. And the other point here is the so-called nadir objective vector or nadir point. And as you can see, it represents the worst values the objective functions can obtain in the set of parallel optimal solutions. This one is much harder to get whenever we have more than two objective functions, but we can estimate it because typically we don't know this set of parallel optimal solutions explicitly. We have only this mapping involving variables and functions. So we usually need to estimate what are the worst values in the set of parallel optimal solutions, because this is not necessarily the same as the worst values in the feasible region. The set might even be unlimited, and still the set of parallel optimal solutions might have this bound. So that's why getting the nadir objective vector exactly is not an easy thing, but as said, we can estimate it. And it brings us some valuable information about the ranges where the function values can vary when we deal with parallel optimal solutions. But we have these trade-offs as said. When one function improves, for example, in this case, the other one needs to get worse. And when we have more objective functions, we still have trade-offs, and it's just harder to visualize. So that's why I have settled to visualize things with only two objective functions, but it's not implying any limitations to what I say being valid for only two objective functions. And this concept of dominance is important. So in the definition of Pareto optimality, we can articulate it in other words, saying that an objective vector dominates another one if there's no component that can be improved without impairing at least one of the others. So in the set of Pareto optimal solutions, they don't dominate each other. And as said, to be called as the final solution, we need to find a solution that the decision maker in question, the domain expert in question, finds the most preferred. So that's the goal, to find the best compromise. And some more reminders. Many times when we deal with this kind of problems, besides the decision maker who is the domain expert, we have an analyst who knows the methods, who knows how to connect methods to software, or we can sometimes even refer to the software as analyst. But the decision maker is a domain expert who doesn't need to know about the methods and their technical properties. The decision maker needs to be focusing on the application in question. And another important reminder that we tend to often limit our attention to Pareto optimal solutions because it doesn't make any sense to find to accept a solution where it would be possible to improve some function without any sacrifices elsewhere. But this limitation makes sense only if we know that there are no unexpressed or approximated objective functions in the picture. So if the decision maker is rational and the problem is correctly specified, the final solution is always Pareto optimal. Then we have this concept of utility or value function that is a mapping from the objective space Rk to real numbers. And in many cases, when developing methods, people assume something about the utility function, and these mathematical properties give them then some possibility to say something about the convergence of the method, for example. This is theoretically a very nice concept, but practically not always that convenient to use, because it is not at all easy to formulate understanding of this kind of a function that would capture the preferences of the decision maker well. So that's why in the methods that I will be talking about today, we are using the concept of satisficing, so that there are preferences that we try to get as close as possible, and we don't assume anything about any underlying utility or value function. And one of the ways that we ask the decision maker to articulate preferences is providing a reference point consisting of objective function values that are of interest, that are desirable for the decision maker. And these components are called aspiration levels. This is just one example, but I will be referring to it several times. So aspiration level is something that the decision maker finds desirable as function value. And then when we formulate multi-objective optimization problems, we can have problems where we can express analytically the objective functions and constraints. On the other hand, we can have simulation-based problems where we have a simulator that simulates some process, for example, or phenomenon, and the output of the simulator is used to derive the functions for the optimization problem. We can also have data-driven problems where we have collected data from some real phenomena, and then we need to fit some meta model, typically some machine learning model, fit this model to the data to derive functions to then get a multi-objective optimization problem to be solved. So we can come up with multi-objective optimization problems from various directions. And before solving anything, it's extremely important to make sure that the problem formulation is good enough. Unfortunately, many times when you look at publications, the authors don't necessarily tell that much about how they ended up with the problem formulation that they are working with. And then it gives the impression that it is something that is kind of a given, and the truth is that sometimes the problem formulation is the step that takes most of the time, and solving the problem proportionally takes much less time to be able to capture the essence of the problem in question in the formulation. So I want to remind of this importance, because the problem formulation matters. If there are problems with it, optimization cannot compensate any shortcomings. And it sometimes has to be an iterative process where we have some problem formulation, we get some solutions, we see whether the solutions are corresponding to the domain experts' understanding about how things are, and we need to iterate. We might need to add some perspectives, that is some objective functions. We might need to reformulate some functions to really come to capture the essence of the problem. In this book chapter, I have shared some experiences related to the problem formulation. And then there's this paper where some steps are articulated to support in making a problem structuring in a systematic way to come up with a problem formulation that leads to a multi-objective optimization problem that we can then start solving. I mentioned data-driven optimization. And this is connected to different types of analytics. I say a few words about this because nowadays the world is full of data, and we can identify data-driven problems in various domains. And we can roughly divide analytics, very roughly, into three types. Descriptive analytics answers the question, what has happened? So it describes some phenomena that is present in the data available. Predictive analytics means that based on the data, we make forecasts. What could happen? Most machine learning methods, for example, concentrate on making predictions. Based on the past data, they make forecasts for the future. The most advanced type is prescriptive analytics or decision analytics that tells us what should happen to get the desired output. And once we combine this with multiple conflicting objective functions, we have, on one hand, multi-objective optimization problem to be solved, and we can make recommendations or suggestions as decisions what should be done to get the desired outcomes. And here is the same in a different way expressed. So we have some phenomenon, and we have collected data relevant to that, and then we analyze the data, utilize all these different layers of analytics, and we identify a decision maker to augment the data and eventually set some goals, what we would like to do with the data, and that comes as a step to articulate the objective functions that characterize the goodness of the decision to be made. And this might need several iterations. We might even need to collect more data to get enough information to consider the problem that we wanted to. Then we have the decision making supported with multi-objective optimization tools. And then we have an answer to the question that we started from related to the phenomena in question. In Jyväskylä, we have this kind of a profiling or thematic research area devoted to decision analytics, where we are building tools for the seamless chain from data to decision making. So we can have different types of data. Then, as I mentioned earlier, then we need to utilize different tools to model the problem. Sometimes we need to pay a lot of attention to causal inference. So what is safe to be concluded from the data, how the data has been collected matters here a lot, to be able to formulate a multi-objective optimization problem and then solve it. And we have considered different domains of application in this context. So now I have said a lot about problem formulation because it's so important that we know what we want to solve before we jump to applying multi-objective optimization methods. But now I'm getting to the point, and I like dividing multi-objective optimization methods into 4 classes based on the role of the decision maker. This comes from the book of Hwang and Masud from the 70s. If we have no decision maker, no domain expert available, then we need to identify some neutral compromise solution. In a priori methods, first the decision maker sets hopes and expectations, and then we try to find a solution that is closest to those. But sometimes it might, even though the decision maker is a domain expert, it might still be difficult to express realistic hopes, and the decision maker might be disappointed at the solutions obtained. On the other hand, in a posteriori type methods, we generate a representative set of pilot optimal solutions and then ask the decision maker to select the one that is most preferred. Of course, this avoids the shortcoming of the previous method type, because the decision maker gets solution candidates to study, so one can see what actually is feasible. But to create a good representation of different pilot optimal solutions gets more and more computationally demanding as the number of objective functions grows. And on the other hand, it gets also cognitively more demanding for the decision maker to digest and analyze a lot of solutions. So that these are some of the reasons why we favor interactive methods, where we have an iterative process where the decision maker takes actively part, and we try to avoid the above mentioned shortcomings. And from now on, I will concentrate on some interactive methods, but before that, I will say a few words more about elements in this. The methods that I will be talking about, they are based on scalarizing functions. The idea is that we combine preference information coming from the decision maker and the original problem formulation and get a scalarized single objective problem to be solved with the appropriate single objective optimization method that is suitable for the characteristics of the problem. And the objective function of this new problem we call a scalarizing or scalarization function. And by selecting this function carefully, we can guarantee Pareto optimality. Because as Savaragi and all have articulated, it is desirable that we can guarantee Pareto optimality, and on the other hand, we know that we can find any Pareto optimal solution by just changing the preferences in the problem formulation. For example, the weighted sum is an example of scalarizing functions that does not necessarily meet this second perspective, because if we have a non-convex problem, there might be Pareto optimal solutions that we will never find, no matter how we set the weighting coefficients. This is a Riemann scalarizing function is an example of the scalarizing functions that we use a lot. This is proposed by Wierzbicki, and it's based on the reference point denoted here by Z bar that represents the desirable function values that the decision maker has provided. And in this formulation, here we have function values, here we have the components of the reference point, and here we have the components of the nadir point, and here we have the components of the so-called utopian objective vector, where we have shifted the components of the ideal objective vector a little bit so that we will never have the risk of dividing anything by 0. So this is a little bit more optimistic than the ideal objective vector. And this rho is a scalar, positive scalar that has a small value, and thanks to this we can guarantee Pareto optimality for the solutions. Otherwise we would only get weakly Pareto optimal solutions. And the nice thing about this scalarizing function is that it works equally well, even though sometimes, depending on the case, the reference point consisting of the aspiration levels could be achievable or it could be unachievable, but it works in any case. So for example, if we have this kind of a problem with two objective functions to be minimized, and once again, these red areas represent Pareto optimal solutions. If the point A is the reference point, by solving this function above, we get this black point, which is Pareto optimal and sort of closest to the reference point by measuring the distance with this function. And if we have B as the reference point, by solving the problem, we get this point, once again, Pareto optimal solution that is sort of closest to the reference point. And what this second part of the function in particular does is that if we, for example, have this kind of a reference point, point C here, and if we once again solve the problem, we would, without this term, we would get this point. And as you can see, it is not Pareto optimal. It is weakly Pareto optimal because we can improve the value of F2 here without any change in F1. So this is weakly Pareto optimal, but with the help of this term, we increase the slope of this cone a little bit to make sure that eventually we would get this solution, which is Pareto optimal. And this is the nice thing with this scarizing function, that I said that no matter how the reference point is given, we always get Pareto optimal solutions. Then I want to say a few words about different types of methods, even though I will not go too much to the other side. So in the field of multiple criteria decision making, as you have heard already earlier in this course, the idea is that we have a solid theoretical background. We can prove Pareto optimality. We see that the role of the methods is to support the decision maker, and in this preference information plays an important role in the solution process. And there are a lot of different types of methods, but also the interactive ones are widely developed. In many of these methods, scarization is used as a part of the method. But to be able to solve the scarization functions, our mathematical optimization tools need some assumptions. And these assumptions need to be valid so that we can really guarantee that the solution we get is Pareto optimal. And in many cases with real problems, these assumptions may not be valid. And there are different ways to overcome this. And one example is to use population-based methods like evolutionary multi-objective optimization methods that are meta-heuristics by nature. So they cannot guarantee any optimality, but they have shown to be working well in many real cases. And the idea is that we have a population of solution candidates, and we manipulate this population to move these solution candidates towards Pareto optimal solutions, so that the population would cover and represent Pareto optimal solutions well, and would be as close to Pareto optimality as possible. Originally, these methods did not really pay much attention to the decision makers' preferences. They were mostly of a posteriori type, so they just wanted to give a representative set of Pareto optimal solutions. But in the recent years, more attention has been paid also to the fact that there might be more objective functions. This kind of approaches can be computationally inefficient when we try to represent the set of Pareto optimal solutions when we have many objective functions. So it has become apparent that incorporating decision makers' preferences in evolutionary methods also makes a lot of sense. So there are also interactive evolutionary multi-objective optimization methods, but I will not talk about them today, but just to make it clear that there are also interactive methods of this type. As said, we can't guarantee optimality, but in many cases they can work well. For example, if we have discontinuous functions where normal mathematical optimization methods would not be working well. And because there is not that solid theoretical foundation in this line of research, they have settled to create a lot of so-called benchmark problems where the set of Pareto optimal solutions is known. And then methods are compared against these benchmark problems, and then one can say which methods work better than the others by formulating so-called quality indicators to represent that. And in that way, it's possible to evaluate the performance thanks to the benchmark problems and the quality indicators. But there are not that many quality indicators that are appropriate for interactive evolutionary methods. So there are various open research directions still. I have mentioned the decision maker many times, and I will be doing so many more times, but I already briefly touched the point that we need the decision maker's preference information to augment the problem formulation, to be able to say which of the parrot optimal solutions would be appropriate to be called the final one, which would be meeting the needs of the decision maker best. So the analyst needs to support the decision maker, and it is important to decide what type of information the decision maker in question is able to provide to express one's needs best. And it has to be understandable and meaningful to the decision maker. And if this is not the case, then we introduce a lot of cognitive load on the decision maker, which is not at all desired. So whatever information the decision maker can provide, we should be able to utilize, but we should not ask questions that are not meaningful or understandable to the decision maker. And then attention needs to be paid, for example, to the user interface, how we communicate, how the method communicates with the decision maker. We need some visualizations to communicate the information, and there are various other perspectives to consider. And also the time, how much time the decision maker can afford in spending with the method. That's also of importance. But now I have laid the basis to get truly to the world of interactive methods. By the way, do you have any questions before I switch to the main theme of my lecture? Silence. Are you still there?
Yeah, we're all here. There are no questions.
As said, I can see only my slides, so I just wanted to make sure that I'm not only talking to myself. So no questions so far, I guess. So I can go on. So as mentioned, in interactive methods, a decision maker is very much needed to provide some additional information as a part of the solution process. And the nature of interactive methods is iterative. So we have a solution pattern. It is repeated iteratively. We show some information to the decision maker, and the decision maker articulates preference information, and then we create some more information, show it to the decision maker, and the decision maker articulates preferences. And eventually, we aim to find the most preferred parrot optimal solution for the decision maker. And because of the active role of the decision maker, it's very important that the decision maker understands what information we communicate with. And basically, in most of the methods, with the help of the preference information, the decision maker moves around in the set of parrot optimal solutions. As said, we should not ask too difficult questions, and we should enable the decision maker to learn. This is a very important aspect, in my opinion, because even though they are domain experts, they still may not have had the opportunity to see the values of the conflicting objective functions simultaneously. And this is offered by the methods that we provide. And they might have optimistic or pessimistic expectations. And it might even seem that they are changing their minds. And this does not necessarily mean that they are irrational. It can just mean that they are learning. For example, it has happened to me with domain experts that before the solution process with an interactive method, they often say what kind of a solution they would like to get, what they would find as desirable. And after the interactive solution process, it seems that they have decided to choose something, a solution that is not at all like the one they described at the beginning. And when they are asked about why did you select this solution, they tend to say something that refers to the fact that they learned about the trade-offs. They learned, for example, that what they were hoping to get, it is not eventually meaningful or feasible. The desired gains in some functions would need too much sacrifices in some other functions, or that what they what they thought they wanted was easy to achieve, so they wanted to pay attention to some other perspectives during the solution process. Many things can happen, and that's the key of interactive methods, that they enable the decision maker to learn and gain insight into the trade-offs and into the phenomenon in question. In this paper, we have summarized various interactive methods for multi-objective optimization. The other side of the coin is that because of the iterative nature of the problem solving, the decision maker needs to have some time and interest to take part in the solution process. If the decision maker is too busy, then interactive methods are not the right choice. The beauty is that we don't try to generate all possible parallel optimal solutions. In this way, we save in computation cost, in particular if the function evaluations are time-consuming or otherwise costly. So we only show those parallel optimal solutions that are of interest to the decision maker. So we also avoid this high cognitive load when the decision maker does not need to digest huge amounts of data at a time. As said, it is very important that the decision maker can learn about the interdependencies among the objective functions, and on the other hand, learn about the feasibility of one's preferences. And one can adjust the preferences. One can adjust and modify the preference information based on the learning. And continue the solution process as long as one finds meaningful. Because of the learning, the decision maker gains more confidence in the solution and also can explain to the others why one ended up with the final solution one selected. As I mentioned before, this communication between the decision maker and the method needs some good channel, and a user interface therefore plays an important role. And we have a plethora of different interactive methods, depending on what is the information we expect the decision maker to provide, what kind of information we provide to the decision maker, and how we generate new solutions based on the information we get from the decision maker. And I don't plan to cover all possible interactive methods. That is not at all my objective today. I have just some examples, but in the big picture, many interactive methods follow these main steps. Not all, but many. We initialize, depending on the method, it can be different, it can mean different things, but for example, we show the ideal and the estimated nadir objective vectors to the decision maker to give some understanding about what are the ranges of the objective functions where the decision maker could find a meaningful solution from. Then we have one starting point or some starting points that we generate in different ways depending on the method, and we show this information to the decision maker, and then we ask the decision maker to provide preference information, and depending on the method, the type of preference information varies. Then we generate new parallel optimal solution or some solutions based on the preference information. We try to reflect the preferences as well as possible. and show this to the decision maker, and possibly some other additional information, as once again depending on the method in question. And then we ask the decision maker to study the information obtained, and in many cases ask to select the best solution so far, which is then to be applied as the starting point of a new iteration, or if the decision maker is happy, we stop. As said, otherwise, we continue by asking for preference information related to the selected solution. This is very rough series of steps, but covers many methods on a high level. I have mentioned the term preference information many times, and I have only given you one example. So I mentioned this reference point, so that the decision maker provides a desirable value for each of the objective functions. They are called aspiration level. They constitute a reference point. It is also possible that the decision maker provides ranges. So basically upper and lower bound for relevant or meaningful or interesting function values for each of the objective functions. So we get ranges. It is also possible that we can generate a small set of Pareto-optimal solutions and ask the decision maker to indicate which of those are desirable. And then we concentrate on more solutions that are alike those, or ask the decision makers to select the solutions that are undesirable, so that we know to avoid that kind of solutions in the future. We can also classify objective functions based on what kind of changes in the function values would make the solution even more preferred. I will get back to what this means soon. We can ask their opinion about marginal rates of substitution. We can have pairwise comparisons. We can study desirability of trade-offs and many more. And why do we have all these kind of different types of preference information? Because different decision makers may prefer different formats and different types of information. And we need to have more than one tool in our toolbox because, as said, having a meaningful way to express preferences for the decision maker is very important to be able to reliably apply the method in question. For example, in this glide papers, we have made some overviews of different types of preference information and articulated some scarizing functions that can constitute various formats nicely. Whenever we study interactive solution processes that decision makers have taken, we can often identify two phases. I don't say that this would be always the case, but in many cases we can identify phases. First, the learning phase, where the decision maker gives different types of preferences to explore what kind of Pareto-optimal solutions there are. The decision maker learns about the trade-offs and can, for example, change the preferences pretty radically to scan different types of solutions for the problem to understand more about the trade-offs involved. And in this phase, for example, a rough approximation of the set of Pareto-optimal solutions can be used to support the decision maker. And eventually, the decision maker identifies a region of interest that one wants to concentrate on. And then we get to the decision phase, where we work in this region of interest. So the decision maker does not dramatically change the preferences anymore, but investigates this region more closely and eventually finds the final solution. Of course, it's possible that after the decision phase, the decision maker goes again to a learning phase. There's no rule to say that this would not be allowed, but as said, this is just observations of solution processes that we can often identify learning phase and decision phase, and many times they go like this: that first more search, and then more focus and concentration on a certain area in the set of Pareto optimal solutions.
Sorry, Kaisa, there's one question.
Yes?
Maike?
Yes, I have a question, Kaisa. How long does this process normally take in practice? Like to get to the learning phase, for instance?
Thank you. Of course, it depends a lot on the case. It depends on the decision maker. It depends on the problem and how well the decision maker, for example, knows the problem in advance. It could be typically not more than 10 iterations in most cases. At least, of course, now I'm only talking about those that I have experience with in different domains with different decision makers. It could be between, sometimes they are, if we are really lucky, they are very happy with what they see at the very first phase, and they don't do that much of learning, so they can jump immediately to the decision phase. That's also possible. But between 1 to 7 iterations, roughly, maybe.
Okay. And how long does it take?
That's a typical. And then in the decision phase, maybe 2-3 iterations. So, and in terms of how much time it takes, it depends on the problem in question, whether the function evaluations are time consuming or whether they don't take practically any time. I will get back to this time consuming element a bit later. Did you have some follow-up question?
No, thank you.
Was this helpful?
Yes.
Okay, good. Thanks for asking. Any other questions? Okay, let me move on. But as said, don't hesitate to ask whenever something comes up that you would like to clarify. So, as I said, preference information is the way we communicate with the domain expert, the decision maker, and it has to be meaningful and understandable. Otherwise, we don't speak the same language. And you know what happens when you don't speak the same language. You are starting to make misinterpretations and you can get into trouble. So that's why I concentrate on some specific types of preference information. The first method to mention is reference point method by Wierzbicki, the same guy to whom I referred to when I mentioned the achievement-carizing function earlier. So, as the name suggests, reference point method utilizes reference points as preference information. And as simple as that, the decision maker provides a reference point. We calculate the solution that is closest to it and show it to the decision maker. For example, if this is the reference point, I hope you still can see my mouse, then the corresponding solution would be this one. And if the decision maker provided this reference point, we would show this solution to the decision maker. But we don't only show that solution, but we show a bit more. For example, in this case, when we have 2 objective functions, we would show 3 solutions to the decision maker. So k plus 1 in general, 1 more than the number of objective functions, because we coordinate-wise shift each one component at the time of the reference point and calculate the corresponding solutions. And the beauty of this idea is that if the reference point was somewhat close to Pareto optimal solutions, this coordinate-wise shift would not dramatically change the components of the reference point. So we would get these 3 solutions. So the decision maker would get a representation of solutions in this area. But if the reference point is, for example, like this, pretty far from the Pareto optimal solutions, the solution corresponding to this would be this one. But because this is so far from the Pareto optimal set, it seems that maybe the decision maker is not that well aware of what kind of solutions actually are feasible and available. Then this coordinate-wise shift of the reference point leads to bigger changes, and then we would have this solution, and this solution shown to the decision maker. So the decision maker would have understanding about the broader range of different Pareto optimal solutions to be able to better decide what kind of solutions one would actually like. And by showing these solutions to the decision maker learns more and then can articulate new reference point accordingly. And this function, this achievement scalarizing function, is indeed the way we get these solutions to be shown to the decision maker. And here's the algorithm roughly. So we typically show ideal and nadir points to the decision maker so that it's easier to provide the first reference point. And then we solve this achievement scalarizing function and show the corresponding solution. And then we shift the reference point as said in k directions and get new reference points and calculate the corresponding solutions and show also them to the decision maker. And if the decision makers find some of these solutions acceptable, we stop. Otherwise, we ask the decision maker to provide a new reference point, and then we get back to step 3, where we calculate the corresponding solution and iterate as long as the decision maker wishes. Very simple method. And the beauty here is that because we use reference points, they constitute of objective function values. And what we show to the decision maker is objective function values. So there is no mapping between these two types of information. The decision maker can immediately see how well the function values that he or she wanted to get can be actually achieved. So this is convenient. Now we move to the next method called Nimbus. As said, this is one of the methods that you will hopefully have an opportunity to apply in the afternoon in the practice session. Nimbus method, once again, deals with objective function values because we can say that they are understandable and straightforward, because if function values of the objective functions are not understandable to the decision maker, then we don't have a correct domain expert available. And in the Nimbus method, we use a so-called classification as the type of preference information. So we show one Pareto optimal solution in the objective space, so the Pareto optimal objective vector to the decision maker, and ask how objective function values should be changed to get a more preferred objective vector. And we have up to 5 different classes available. And so the decision maker decides which class to select for each of the objective functions. And the classes are for functions that should be improved as much as possible from the current level, functions that should be improved till some aspiration level, but not beyond that, functions that are satisfactory at the moment, functions that can be allowed to get worse till some bound to make room for other functions to improve, and functions that can be allowed to change freely for a while. Remember that based on the definition of Pareto optimality, it is not possible to ask for improvement in all objective functions. We need to allow some function to get worse. Otherwise, we won't be able to go anywhere from the current solution. So we need to have some functions in the classification that we ask for improvement, and we need to allow some functions to get worse. That is what we mean by a feasible classification. And this search continues as long as the decision maker wishes. There's also a possibility to generate intermediate solutions. So if with different classifications, the decision maker has obtained two interesting solutions and would like to see what kind of Pareto optimal solutions can be found between those, the system can also create that kind of options. And to get the Pareto optimal solutions, we have a scalarized problem to be solved with an appropriate single objective solver. Here are some papers about Nimbus, but this is not all. Here is an example of the scalarizing function that utilizes the classification information that we solve to get a Pareto optimal solution. And this term here, once again, as before, is there to guarantee that we don't get weakly Pareto optimal solutions. We can prove that if the solver works well, we get a Pareto optimal solution by solving this. And any Pareto optimal solution can be found by changing the classification. And by seeing the solution of this problem, the decision maker can check how well the preferences were able to be achieved. So one can get the feedback of trade-offs and modify the classification in the next iteration. Nowadays, we don't only use a single scalarizing function, but we typically use a so-called synchronous version of Nimbus. Because we observed that even if we provide the same preference information, if the scalarization functions are somewhat different, we would get different solutions. And then in a way, the method developers decide what solution is to be shown to the decision maker. So we have decided in the synchronous Nimbus that we have up to 4 different scalarized subproblems that we form based on the classification information that the decision maker provides. And by solving these problems, we can get up to 4 different Pareto optimal solutions. And we show them to the decision maker. Instead of us deciding which of these solutions would be the best, we let the decision maker to choose. Of course, if the decision maker does not want to compare, it is still possible to only say that I want to get 1 Pareto optimal solution per iteration. But this gives more flexibility to the decision maker. So we have this classification, we have intermediate solutions, and we can decide how many solutions to compare after each iteration. So the decision maker can decide to which extent one utilizes these opportunities. And the main idea is that the decision maker learns. It's interesting when we have studied, for example, the reference point method and Nimbus with different experiments involving, in particular, students in Malaga as decision makers, that even though reference point is so simple, you just provide a reference point and see what happens. And Nimbus, where you have to provide the classification, these decision makers have mostly preferred Nimbus, even though it's a bit more complicated. You need to make sure that the classification is acceptable and feasible, but it enables you to learn more when you think a bit more about the preferences and what actually you would like to achieve. And that is an interesting observation. So once again, the algorithm in brief, we need to choose the starting point because, as said, we need some objective vector as the starting point for the classification. If it's not Pareto optimal, we make sure that it is, because otherwise this does not make any sense. So the decision maker starts with some Pareto optimal objective vector, and we ask for the classification, and then also allow the decision maker to decide whether to apply 1, 2, 3, or 4 subproblems, or we don't ask it in this way. We ask only whether you would like to see 1 to 4 new solutions that correspond to your classification. Then we show these solutions to the decision maker and allow also the decision maker to save some of those to be returned to later. So they would be going to the database. And If the decision maker wants to see some intermediate solutions, then we ask which would be the two solutions between these two. We will then generate the desired number of intermediate solutions. Or if the decision maker doesn't want to see intermediate solutions, we ask the decision maker to select the solution that one would like to use as the starting point for a new classification. If intermediate solutions were asked for, we generate those and make sure that they are parallel optimal and show them to the decision maker. And we ask the decision maker to choose the most preferred solution. If there is a desire to continue to make a new classification, we can allow that, or otherwise we declare the most preferred solution as the final one. So the decision maker decides how many iterations to take. In 1995, I guess most of you had not even been born, but we had an implementation of this method operating over the World Wide Web. And it was nice for us because we had one version, centralized computing distributed interface, where these kind of key concepts. It was basically the very first existing optimization tool that was operating over the internet in those days. Nothing to install, just apply the tool over the internet. But then we had to implement a version that was operating in Windows and Linux systems, because people in those days didn't feel comfortable in communicating their information over the internet. And we connected that to different simulation tools, for example. But now we are in the third generation of Destio, where we have this open source software framework that contains, for example, Nimbus, but also other interactive methods. And I will soon tell you more about the Destio. But before that, this is what the homepage of Web Nimbus is like. Actually, it is still available. You can still apply it to check how it works. It has this kind of visualizations, for example, to compare different parallel optimal solutions. And this is what the UI of IntNimbus looked like. On the left-hand side, classification, the solutions generated to be shown on the right side. And also there are some ways to visualize solutions. I was briefly mentioning something about computational cost before. Now I'm getting back to that topic. But before I go there, are there any questions about what I said so far? Okay, either you are fully on board or you have fallen asleep. I hope it's the former and not the latter.
They all look awake.
Pardon?
They all look like awake. So
excellent. Excellent. That's comforting. So let me move on and get back to the situation. What if function evaluations are computationally costly? For example, if we have a simulator that we need to run before we get objective function values for our problem, this might take time. For example, we might have some computational fluid dynamics system to be solved to get some function values. What to do then? We need tools that can handle these kind of cases. So if the function evaluations are time consuming, or we can have black box models where we don't know exactly what kind of solver would be appropriate. One way to handle this is to train a computationally inexpensive surrogate model or meta model for each of the expensive functions, and use this meta model instead of the original function. And in this meta model would be then not slowing down the solution process. We would be able to have calculations basically in real time. That is one option, but one can do this also in different ways. And now I will say a few words about that way. It is all about hybridization, so that we combine ideas of different methods and create new methods where we try to utilize the benefits of the individual different methods that we are combining to avoid some of the weaknesses. That's why we hybridize ideas. And one way to do this is to consider a posteriori methods, where we get a representative set of parrot optimal solutions, and we can generate this set without involving the decision maker. In that way, we have information about the whole parrot optimal set, and we can connect an interactive method to that, which enables learning, which enables gaining insight into the problem, and concentration of on the solutions that are of interest, and saving computational time as well. So I will say a few words about the hybrid of a posteriori and interactive methods. Of course, one can also make hybrids of different types of methods. These are just examples. The big picture is that we have basically 3 stages. The first stage is that we apply an a posteriori method and can get a set of solutions that are parrot optimal or nearly parrot optimal. If we apply, for example, an evolutionary a posteriori method, as I mentioned, we might not be able to guarantee parrot optimality, but anyway, they are close enough. And based on this information, we can create a surrogate problem where we take this surrogate problem to be solved with an interactive method involving the decision maker. And because the surrogate problem is computationally less expensive, the decision maker does not need to wait for new solutions to be generated, and the decision maker can still control the solution process conveniently and come up with some solution that utilizes the surrogate problem as the foundation. And because of that, the solution to the surrogate problem is not necessarily parrot optimal to the original problem. So this takes us to phase 3, where we project the solution to the space of the original problem to get a solution to the original problem. So this kind of 3 stages we can identify. And one example is navigation methods. We have 2 that in these papers are articulated: Pareto navigator for convex problems and non-convex Pareto navigator, well, as the name suggests, for non-convex problems. But they have the same idea, that we first apply an a posteriori method to get a set of Pareto optimal solutions. And based on this set, we create an approximation for the set of Pareto optimal solutions in the objective space, and we enable navigation in this approximated space. And navigation means that we show in real time to the decision maker how function values evolve. And the preference information is based on a reference point. The decision maker provides desired values for the objective functions, and also bounds not to be exceeded, and then sees in real time, when we start from the current solution and start moving towards the preferences, how function values evolve. And this can be shown in real time because we have made the calculations in advance. The decision maker can learn about the trade-offs nicely and as said, see things in real life. And if it takes a long time to create this set of Pareto optimal solutions, we don't involve the decision maker at that stage. It can take a week, and the decision maker would be doing other things. So the computationally costly phase is separated from the interactive phase. And at the end, we can project the solution to the original Pareto optimal set. So in this case, instead of approximating objective functions, we directly approximate the set of Pareto optimal solutions. Here is a screenshot where we have this pre-generated set here in this area surrounded by red. And then we have a preference information aspiration levels for each of the objective functions represented by these blue horizontal lines. This problem has 4 objective functions, and these curves show how the values of individual objective functions have evolved based on this preference information. And if the decision maker, for example, gets interested in some of the solutions, one can click it and then see what are the solutions and then how they are mapped to the true problem. So this is the projection phase. And if the functions are computationally expensive, it might take a while to get this. But as said, it is possible. And then the decision maker can at any time go back, provide new preferences, and navigate in that new direction. And this is what it looks like in 3D. So we have here created the set of Pareto optimal objective vectors, in this case of 3 objective functions. And these black dots are the representation of Pareto optimal solutions that we generate. And here on the right-hand side, we have this approximated set that is based on these points that are marked with black. And then this is the path of navigation shown in this view that the decision maker has taken. So one can kind of drive around the way one wishes. So far, I have talked about the methods that are using Pareto optimal solutions. As I mentioned at the beginning, if everything is well articulated, we know that we should end up with a Pareto optimal solution. But do we need to work with Pareto optimal solutions throughout the whole solution process? What if trading off is not desirable? And to answer this, we have developed a family of so-called Nautilus methods. The tricky thing is that we humans, we don't like losses. And it might be that to be able to move from one Pareto optimal solution to another one, as we know by the definition, we need to allow some of the objective functions to get worse. And if this idea is too painful for the decision maker, it might mean that we are stuck in that area of that solution. And we are not able to move away because we don't like the idea of sacrifices. Our past experiences affect our hopes. And according to the so-called prospect theory of Kahneman and Tversky, we do not react symmetrically to gains and losses. We tend to hate losses more than we love gains. And as said, there might be this danger that we get anchored around the solutions we have seen, so we might fix our expectations, and we are not able to make free search anymore. So based on this foundation in the Nautilus methods, we do things the other way around. So we start from something bad, typically an estimated nadir objective vector, where all the objective functions have lousy values. And then we start gradually moving towards Pareto optimal solutions. And what this means is that we can improve in each of the objective functions simultaneously. So no painful sacrifices, only wins. And what we need to decide is in which proportions we improve the function values. And all the solutions that are shown on the way, they are not Pareto optimal, because otherwise it would not be possible to improve all the function values simultaneously. Only the final solution, once we reach the set of Pareto optimal solutions, that is then a point where we can't go on anymore with that idea. And we can always go backwards, as I mentioned already with the previous method. And from the nadir point, we can basically approach any part of the Pareto optimal set according to the wishes and preferences of the decision maker. And then, as said, we have different variants of this Nautilus frame family, where we have different types of providing preference information and different ways of calculating the solutions. But the idea is always the same, that we start from something bad and then we gradually approach parrot optimal solutions. We need to remember that we operate in the objective space, and we show solutions to the decision maker that do not necessarily have any corresponding solution in the...
Excuse me, Kaisa, I think there's some question in the room.
Okay. Go ahead.
Yes, I was just wondering, the Nautilus method is like we focus on each objective function and improving, but it sounds like a psychological trick for decision maker. We obviously doing the same as was before doing, just to showing to the decision maker that we actually improve in each objective function, but in the end, it's anyway some sacrifices and some improvements. What is the difference actually on this method of Nautilus?
As said, in this way, we avoid anchoring, because there is no temptation to get stuck at a solution where we know that we can still improve all the objective functions. So we avoid the anchoring. We avoid the painful idea of sacrifices. It allows us to find more freely the solution of the parrot optimal solution that we actually want, because whenever we deal with methods that only work with parrot optimal solutions, there is this danger that the decision maker gets anchored around the starting solution. And then it becomes an issue how we select the starting solution and how to make sure that it does not lead to premature anchoring.
Yeah, but is it possible at all to find the solution when all the objective function actually improves a bit? Is there any kind of decision like that?
It is the path we take that is completely different. We end up with the parrot optimal solution, but it's the path that makes the big difference. I will show some figures soon, so maybe that will also be helpful in understanding the point. So if I continue and then you ask for clarifying questions once you have seen a bit more, is that okay?
Yeah, it's okay. Yeah.
Thank you. So, as said, on the path when we are still moving from the nadir point towards parrot optimal solutions, we show objective vectors that do not necessarily exist because we don't keep the connection to the decision space. But whenever we have show a solution, we know that there exists a parrot optimal solution that dominates the one that we have shown. So there is something better available. So in that way, we can assure the decision maker that they are not being misled. And as said, in this way, the decision maker does not need to trade off. One does not need to think of sacrifices. And this is, for some decision makers, really helpful. So this is a new perspective to solving multi-objective optimization problems. It is just one more tool to the toolbox. As I mentioned, it is good to have different methods available that serve the purposes of different decision makers who are comfortable with various types of providing preferences to direct the interactive solution process. And once we get a parrot optimal solution at the end, if so desired, we can continue from that solution with an interactive method. For example, we can continue from that solution with Nimbus and switch from trade-off-free method to trade-off-based method to fine-tune the solution in that area and consider trade-offs. So we don't need to, so in a principle, we can also see this Nautilus method as a way to find a starting point for methods like Nimbus that operate with parrot optimal solutions, so that that there is no danger if we anchor around it, because we have had this phase of free search beforehand, so we are consciously choosing that starting point, and there is no danger that we are missing some relevant Pareto optimal solutions along the solution process. So we have different variants, as said, and they all have some different working principles, but still apply this big main philosophy that we improve until we get to the Pareto optimal set. And here is the figure that hopefully helps a bit. Once again, two objective functions to be more easy to visualize. And the set of Pareto optimal solutions is here like this. And the nadir point is this one where we get started. And depending on how we express the preferences, we determine the direction where we move. And for example, we get this solution, Z1. We have approached the set of Pareto optimal solutions a bit. And this means that from this solution, we can only get to this area in the Pareto optimal set without sacrifices. So we can no longer get to these solutions here, because that would mean a sacrifice in some of the one of the objective functions. And this so-called reachable ranges for the objective functions, they are now here highlighted from that Z1 solution by this red areas. So the function values of F1 can vary between this area, these values, and the function values of F2 can vary between these values. And then once we move on, here we have changed the preferences. So the direction has changed and we have taken one more step. And now the ranges of the function values that we can still reach are indicated by this information. And eventually we get closer to until we get a Pareto optimal solution. And in this way, as said, we can always improve in all the objective functions until we reach the Pareto optimal set. And these reachable ranges, as we call them, they keep shrinking until we get a single solution. And if we at some point notice that, oh, this shrinkage of the reachable ranges is not acceptable, actually I don't like this anymore, one can always get backwards, go to the previous solution, and in that way widen up the reachable ranges again and provide new preferences from that point to move to a different direction where the reachable ranges would shrink in a different manner. Is this helping? I hope so.
Hold on a minute.
Yes?
Yes. Can you state it that, for example, in Nimbus method, it's somehow easier for the computational person, like for us, than just now dealers, because we already have to keep in mind what's the direction of the decision should go, and we need to keep in mind what is the Pareto optimal acceptable, so we could navigate the decision maker, so we won't go somewhere wrong direction. Isn't that more difficult actually to make in life, to make it work?
Well, remember that we develop these methods for decision makers. We want to support them, and whatever, and I will come later to the question of how to select the method, because that's the idea, that we need to have different options so that there is something to choose for the decision makers. And what mindset is easy or understandable to different people, that's exactly why we need to have different options, so that they would each get the method to communicate with the information that is comfortable and understandable to them.
Okay.
And I can see that you are now kind of you started to like the working with Pareto optimal solutions, and now that I have twisted your world upside down, it does not seem comfortable. If I had started with this type of methods, who knows, maybe you would then find Nimbus very clumsy, who knows. but this is the thing that not the idea is that not everybody needs to love all these methods. We just should have different options available so that we can find methods that suit the personalities and preference styles of different decision makers to whom we want to offer these to support their decision making.
Okay, I got it.
Thank you. Then I have mentioned navigation methods. I have mentioned Nautilus. So the natural way is to hybridize these two ideas, which takes us to Nautilus Navigator, which is the other method that you will have the opportunity to apply later today. So it combines these two philosophies. And because it's navigation method, it has a set of Pareto optimal solutions in the background. Once again, this set is generated before involving the decision maker. So if this phase takes time, the decision maker does not need to stand waiting. The decision maker can do whatever one wants to do in the meanwhile. All this happens in the background. And then the decision maker navigates in real time, but in this case, from the worst possible Pareto optimal solution, from the first possible towards a Pareto optimal solution. And we here visualize the reachable ranges that I mentioned earlier, that they keep shrinking as we approach the Pareto optimal set. And we show the shrinkage. And once again, the decision maker can provide preference information to direct the direction where to go. And the preference information type is a reference point or components of aspiration levels, components of it that are called aspiration levels, and bounds that should not be exceeded. And as before, it is possible to go backwards and change the preference information. And it is also possible for the decision maker to decide the speed of movement, whether it goes faster or slower. And we even have a YouTube video of this that Kuro has narrated. But here is a screenshot of the idea that when we start, for example, here we have 3 objective functions. So when we start, the reachable ranges are the widest possible. And once again, these blue horizontal lines represent the aspiration levels. And once we start moving towards these values, the reachable ranges start shrinking. We can stop at any time. And for example, here, this aspiration level has been changed. This one has changed. This one has stayed the same. And we keep until we reach a single solution, in which case we get Pareto optimal solution where we can't continue improvements anymore. Okay, I don't plan to introduce any more interactive methods, but you can be sure that there are many more around, but I don't want to confuse anymore. So I want to switch to the topic of visualization. I will not go to any deep waters in this, but still some ideas about this. A decision maker is often expected to compare different objective vectors. For example, in Nimbus, if the decision maker says that I'm willing to check 4 solutions corresponding to my classification, this means that the decision maker needs to compare the solutions once they have been calculated. And what kind of visualizations to apply to support the decision maker, that's not a simple question, because once again, we humans are different also in this respect. Some graphical representation and tables that contain exact numbers, they are typically seen to complement each other, so they should be both available. But it is not always easy to create visualizations that are both easy to understand and that don't introduce some additional information that was not contained in the original data to be visualized. And the more complicated the visualization get, the more time it takes from the decision maker to learn to actually interpret them. So we have this trade-off once again. It has to be understandable, it should be accurate, and as said, we have different preferences. Some people find some visualization more understandable, the others like something else. So once again, we need to have some options. We have introduced this term interactivized visualizations. Interactivized is not I don't think this word existed until we started using it. But the idea is that when we have interactive methods, we should have also interactive visualizations. So interactive to the power of 2, we called it interactivized, so that the decision maker can also control the appearance of the visualization. That is what we mean interactive by interactive visualization. So the decision maker can affect the appearance of the visualization, what is visualized, etc. Some more information about visualizations is in this book chapter. And for example, here is I guess you are all very familiar with this kind of visualization. This is a so-called value path or parallel coordinate plot. It has many names, but for example, in this case, we have different colors representing different objective vectors, and the bars are the functions. And for example, if all the functions are to be minimized, whenever the paths cross, it means that we have non-dominated solutions, that they don't dominate each other. Of course, we can use bars, we can have different star coordinate plots, so there are a lot of different options. Petal diagrams. Some people say that these are, for example, better than star coordinate plots because here we divide this circumference into as many parts, sectors as we have objective functions. For example, in this case, 3 objective functions, and we connect the function values like this, and it kind of, for example, in this case, it gives us some triangles, and we tend to think that somehow this area represents the solution. But as you know, the order of the objective functions will change the appearance of the area, and it can be a bit misleading because now the visualization, the appearance depends on the order of the objective functions. So the petal diagrams are handling this so that we have these kind of petals, and the order of the objective functions in the visualizations does not change the appearance, the overall area. So these are the kind of examples to think of when we start visualizing solutions. This is a scatter plot matrix. The more objective functions we have, the more segments we have in the visualization. If we turn this parallel coordinate plot so that we combine these extreme parts, it becomes this kind of a figure that can be very compact, assuming we don't have too many of the objective functions. So many things one can do, and for example, here, instead of having a lot of groups of bars, we can have them in 3D. many things one can do, but there are also, all these are somewhat straightforward to digest and interpret. There are also many more, much more advanced visualizations. But as said, the thing is that when then the decision maker needs to take some time to understand how to interpret them. And that's basically a word of its own to develop that kind of matters. I give you an example of score bands as an example of visualizations. So whenever you look at papers, you see this value part of parallel coordinate plots used a lot because they are somewhat fast to learn to interpret. But if we have many objective vectors to visualize, it can easily become a mess. For example, let me show you an example. I have here a plot that is not that easy to digest. It has roughly 140 objective vectors, a lot of crisscrossing, a lot of information, but not that easy to digest the main trends. So the other thing is that it's not that easy to understand correlations among the objective functions in this kind of settings. And that's why we have introduced score bands. So where we group objective vectors and represent the main information in a visually appealing way, and also want to support a gaining understanding about the correlations of the objective function so that we change the distances of the axes, which typically are always constant in parallel coordinate plots, but we provide information in these distances. And then we provide an interactive visualization where the decision maker can very much control the appearance, what to see. And for example, in this case, as said, this is the starting point, and this is what score bands looks like. So we have identified that these solutions can be clustered to three clusters. And isn't this much easier to digest the main trends of these solutions? And you see that the distances are different. For example, these four functions, they are all close to each other, and there's not that much fluctuation in the function values. Then we have this group, and then there's more crisscrossing between these groups. So we get information about the correlation, and we get information about the main trends, how the function values actually behave. And then once we have seen this kind of a overview, one can decide whether it wants to see more details of each of these bands, and in that way gradually add more details if so desired. If we just ignore the bands but show the colors and which are the actual objective vectors that belong to these bands, it looks like this. So anyway, this is much more easier to digest at first, and then, as said, go to details and, for example, say that I want to see what kind of objective vectors belong to this blue band instead of seeing all the solutions at once. But now something about Destel. As I mentioned, it is an open source software framework that we have been developing at the University of Jyväskylä for several years. It concentrates on interactive methods because it is not that easy to find implementations of interactive methods out there. So we wanted to fill a gap. And it's open source. So basically anybody can contribute to it. It is modular by nature, so it is also easy to extend and, for example, add new methods utilizing the modules that are there, implementing only those pieces that are not there, and in that way more conveniently add more methods. The fact that we have different methods in the same environment opens up also new opportunities. It's possible to apply different methods to the same problem, because whenever we typically apply methods, we need to take steps of introducing the problem formulation to different environments. It's time consuming, but once we have added the problem in this environment, it's convenient to solve it with different methods. It's also possible to switch the method between the solution process phases, and it's also convenient to compare different methods. I was referring to some of the comparisons we have conducted earlier. And we are paying more and more attention to the user interfaces and visualizations. But the development continues. And whenever, if you have worked with any software, you know that there are always some improvements. There are new versions. There are some changes being made, and we need to keep this up to date. And on the other hand, our own needs are evolving in terms of what we want the software to be able to do. So every now and then we need to make a more serious re-implementation activity. We are at the moment doing that. So that is why we have now only 2 methods available for you, and there are some things that are not fully functional. So I ask for your understanding that this is a part of the process, but we still wanted to give you something to test with. But I just wanted to give you a warning that it is in the middle of this kind of a more serious re-implementation phase. Here is an article about it. We are about to write another one once this new generation of Desteo is ready. You will get credentials. Maybe you have already received credentials to enter the system. Once you enter it, this is the first page to see. And with the credentials you can access, and on this page you first need to select the problem. Clicking this problem icon here leads you to the list of problems, and we have provided a set of problems, and we have 2 versions of each problem. As mentioned, Nimbus and Nautilus Navigator operate differently. So if you want to apply Nautilus Navigator, you need to select the problem that has discrete in its name, because we need to have this set of parallel optimal solutions in the background. If you want to use Nimbus, you select the problem that does not have the word discrete in its name. Once you have selected the problem, then you need to click here to select the method. And then, as said, you have 2 options. And remember the type of problem you have selected, you select the method accordingly. You click either of these, and then you click up here, solve the problem, and then it takes you either to this UI if you selected Nautilus Navigator, or a different UI if you selected Nimbus. So this is the first view of Nautilus Navigator. And what do you see? On the left-hand side, you see an option to provide preference information. So the blue bar is to provide values for aspiration levels. The aspiration levels give you the direction, in which direction we would start moving, and this other bar is about bounds, and they are visualized here on the right-hand side. So for example, in this case, the objective functions are, for example, the first objective function is to be maximized. So the bound is a lower bound. So it tells to the system the values that should not be exceeded. So the function values should not go any worse than the bound. And if you don't touch it, then the bound stays here and it does not limit the movement. But you can also change it, and by moving this blue value, it gives the direction where you start moving. And once you have selected this, drag these buttons to set the values and clicked the button to iterate, then you start seeing in real time how these reachable ranges actually evolve. And there's a button that's not visible here, but there's a button where you can pause at any time. For example, this has been paused here, and then you can take this circle here and drag to any part in the history to go backwards and provide new preferences to continue from there to a new direction. And these colors represent different objective functions, and you see how the reachable ranges keep shrinking. And if you continue till the end, you will get a single solution that corresponds to the parallel optimal solution that you have found. A word of warning that once you have provided these preferences and once you click the button to start iterating, this phase takes a little while because there are some calculations being done at that point. But just it should not take too long, and then you start seeing how the function reachable ranges start evolving. If you selected Nimbus, you will see this kind of a page where we have one bar per each objective function. And once again, the preference information is to be provided on the left-hand side. And in this case, we have three objective functions. They are all to be maximized in this case. So the bars start from this end, and the interpretation is that the less color you see, the better the function value is, because you want it to be maximized. It should be closer to this end if you want that function value to be very good. So the classification means that the current function values are shown with this length of the bars, and if you want the function value to be improved, you click anywhere on the bar. If you allow it to get worse, you click outside the bar. If you like the current value, you can click this triangle up here. If you want it to get as good as possible, you can click this arrow. If you don't touch it, if you click here, it means that you allow the function values to change freely. So this is the graphical way to tell the system what the classification is. And you need to do the classification for each of these objective functions. So you decide whether you want it to get better or whether you allow it to get worse, and you click accordingly. And then once you are done, you click the iterate button, and then you will see solutions on the right-hand side. And one important thing is that here there's a number, a maximum number of new solutions that you want to see based on the classification. So the upper bound is 4. It can be lower. If you leave it to be 1, then you will see only one solution after the iteration. This is your choice to decide. And it does not, if you say 4, it might still only give you 3 solutions, because it's not always the case that each of these categorizations would give you a different solution. But in this way, you get something to choose from. And if I go to the next slide, if you scroll the page, you would see this table of the function values, so you can see more clearly what the options are. And by clicking here or clicking here, whatever is emphasized is the same solution. And this is the forest problem, and it shows also what the solutions are like in the decision space. we typically tend to only work with the objective space, as I mentioned at the beginning, but for this problem, we also show what it means in the decision space. And as said, how to choose the method matters. The characteristics of the problem, how much time there is available for the solution process, whether the decision maker is available, and if so, what type of preference information the decision maker can provide. All these are elements of choosing the appropriate method for each case and for each decision maker. And an observation, typically in the literature, people report only one method being applied throughout the whole solution process. But we have some evidence and some practical situations where we have seen that different methods may be suited for different phases of the solution process. For example, navigation type method might be convenient for the learning phase, and Nimbus type method could be convenient for the decision phase. So it can offer more flexibility to the decision maker if we allow the decision maker to change the method, that is, to change the type of communicating with the method during the solution process. I can now see that I don't have really much time to say anything about the applications. I had some examples here, but they are, for example, in the field of different processes, controlling processes related to forest treatment planning, related to optimal shape design, related to some health matters, radiotherapy treatment planning, and finding the best exercise therapy for knee osteoarthritis patients. We have worked with various applications, and typically the experiences we have obtained from the domain expertise.
So we have one question here.
Yeah, okay. Please.
Yes.
Yeah, it's about the software online application. I believe that everyone found it difficult to find where exactly we log in. We were trying to find this software online, and where exactly the link to the. You found it?
Yeah, I will send you the link now, so we can start maybe in the next session. We can do a live demo. I'll send you the link. You can have your laptops with you, and you can, because you already have the credentials, right?
Yes, we have credentials, but we couldn't find the login page.
Yeah, so I'm going to send you the link during the rest, so we can start the next session by having some demo, so that you can see how it works live, okay? And you can use the link and your credentials and also practice at the same time, okay?
Thank you. Thank you.
Okay, so I was saying about the experiences from decision makers in applying interactive methods, that they typically like the fact that they can actually consider the different objective functions simultaneously. They can learn about the interdependencies. They can actually gain insight about the conflicting properties in the problem, gain new insight and more understanding about what kind of preferences are feasible. Typically, they have said that the methods have been easy to use, and they have supported them to find a satisfactory solution that they can also explain to the others why they have selected it, because they have gained confidence during the solution process. And finally, some words about what we are doing in our research group at the moment. We are hybridizing different things, using different AI tools as well. For example, explainability, to give more insight to interactive methods. We are working with different decision analytics problems, paying attention to comparing interactive methods, for example, quality indicators and different experiments, more about visualizations, getting inspiration from different real-world problems, paying attention to uncertainty. what I have said here, I have ignored uncertainty and assumed everything to be deterministic. In real world, this is not always the case. We are also considering how to support a group of decision makers who might not have all the same preferences, and we continue developing DEST. So to conclude, there are a lot of applications out there that need to be solved with multi-objective optimization methods. And if the decision maker is available to take part in the interactive solution process, they can gain more insight. Many times one can say that the learning that takes place is even more valuable than the final solution. We can incorporate preferences in different ways, and this means that we have different methods that we can choose from. I gave some examples of hybridization. There are many more. I emphasize the importance of the appropriate problem formulation, and mentioned also how to select the methods. It's also useful if we give the decision maker an opportunity to change the type of providing preference information during the solution process if the decision maker so wishes. And my final claim is that the compromise is better than optimum. In layman's language, we tend to say that compromise is something negative. I had to make a compromise, people tend to say. But still, by considering conflicting objectives and finding the best balance is much better than simplifying the problem to the extreme where we can only have one function to be optimized. Thank you.
Okay, thank you, Kaisa. You're getting an applause. It's muted, but you should know that.
Yeah, now we can applaud.
Okay, so like I said, I did not